Okay, so here is the inside of the actual sweep generator, okay, with the 6J6 in the middle here. Yeah, if I remember correctly, a 6J6 is a double triode. Now, you'll remember, hang on the description they say, hang on, they say back the capacitor plates C10A and C11A all the way out. Okay, and they even they add that there are two small screws to that effect near the stator plate lips. Okay. So what they actually mean is this. Right here and right over there you see two little screws, okay? So here and there. And these are the C10A and the C11A screws, or capacitor screws they are talking about. Actually, I don't know if you can see this, but if you look quite closely at the screw, you'll notice that it is not encased in metal, but there is a kind of well, I would say plastic material around it, or maybe even bakelite. I can't really tell, but these screws are actually insulated from the chassis, okay? They don't touch the chassis. So according to the explanation for the alignment of the sweep generator, I should back out those screws, and then I should set the sweep width control, which is that button here, for maximum sweep range. Okay, so all the way to the right. Okay. And then they say I should screw in those two little screws, the C10A and the C11A capacitor screws, by equal amounts. So I should turn them in symmetrically until the marker appears in the center of the trace. Now remember, on my output of my sweep generator, so right here, there is that small demodulator print board I built in. Okay, so essentially the signal output on the scope would be a flat line. I'll switch it on for a moment to show you what they mean by a flat line, but you'll notice it's not as flat as they show you here on the picture. Actually, if you have a proper marker generator and you would inject a marker, you would get a little tip or a little marker somewhere on this line, okay? And the goal is that you should screw in those two little screws, a bit more or a bit less, so that the marker, which by the way is set at 195 megahertz, would appear right in the center of this line. Okay? And then you should go through several cycles of doing this, you know. They do say that you should be very careful not to turn down those screws all the way down, because it may short circuit the B+. So if you're thinking of doing this with your own sweep generator, beware, because if you short out the B+, that might create quite a spark. Okay, anyway, they say that I need to go through this cycle again and again and again for starting from channel 2 all the way up to, I suppose, channel 9, or even further. I could go all the way up to channel 13, I suppose. Now, this is where I have a problem. My marker generator, my heatkit marker generator, is incapable of generating continuous markers, and I suppose I could have tried to inject via my high frequency generator a variable signal into the marker generator, and that way try to generate a continuously changeable marker generator, but I noticed I did not have enough pigtail cables to do that. So yeah, well, that too is a problem. Okay, so it gets a bit complicated. Anyway, I did give it a try, okay, and let's say at least I got the deep modulated signal of my sweep generator on the scope, and I'll show you that next. And that's where I kinda, you could say, hit a brick wall. So what I'll do now, for now, is I'll show you the signal, and then I'll just finish working on the sweep generator, because there are two things I still need to do. First of all, I noticed that the sweep control, which is a potentiometer right there on the inside, okay, and it has a kind of a gap, meaning that if I turn the sweep action all the way to maximum, there comes a point where the sweeping simply stops, and when I continue turning the knob clockwise, it suddenly resumes, but a lot harder. In other words, there is a gap somewhere in that potentiometer, so I need to unmount it and have a good look at it to see what's the trouble. Also, like I said a few minutes ago, the little adapter I built in on my attenuated RF output is wired as a demodulator right now. But if I want to use my sweep generator as an actual sweep generator, I need to disable the two diodes on that little module. So I need to do that as well. And then there's a last little issue still. Well, I can't really say whether it's an issue or not, but there is still 1 voltage inside my sweep generator, which doesn't seem quite correct, and I want to see whether I can correct that problem, because I think that might improve the output strength of my sweep generator. So let me show you next what kind of signal I'm getting now on my scope. And that's the signal you get on the scope. It's not what you could say a very clean line, but it's reasonable. Okay. Anyway, the goal would be to get a marker on top of that line. Yeah, and I can simulate what they mean by showing you with my heat kit marker generator. Okay, so you would get something like this on the signal, and a small marker pip like this. You see in the center of the screen. Yeah, so the goal would be to have such a marker on the swept, the demodulated output of my sweep generator. Okay, so which would be a flat line as it is right there. Okay, and then to superimpose or to inject a marker on top of it, something like that. Okay, so that would be the goal. Now, like I said, this is only a simulation, okay? Because like I said before, I just can't get the right frequency I would need to do the job. Yeah, the highest frequency I can generate is 139 megahertz and a quarter, and not 195. That's the first problem. Secondly, this is just a superimposed high frequency signal, and I don't know whether I could call that a proper marker. Okay, so anyway, I'm really not happy with the setup as it is right now. So what I did is I ordered a couple of pigtail BNC connecting cables like this on the internet, and when I have them, I'll give it another shot, albeit not on channel 10, but maybe a lower channel, and I'll use an external marker generator, meaning I will connect up my high frequency generator, which you see over there, to this input here, and then I can generate a marker at any frequency I like. However, my function generator, my RF generator you see over there, can only generate up to 110 megahertz. So I would be bound to at most channel 6 or somewhere around there, and I wouldn't be able to align all the higher channels. So until I get a proper marker generator and a proper high frequency generator, I'm afraid I'll never be able to give my sweep generator a proper alignment on all the channels. So that's where I stand right now. Now, what I'm going to do now is, like I said before, I'm going to have a look at the sweep width potentiometer, which I think you can hear. Now it's at maximum. See what happens when I turn to minimum counterclockwise. There, you see, it died. And now it resumed, but it's much more quiet, so it's far less. Anyway, there's a dead point somewhere between 8.5 and 6, roughly speaking. So I need to find out what that problem is, and then we'll modify the RF adapter board I built inside, and we might have another look at that voltage problem on one of the tubes. I think it's on the 6C4 tube. According to the schematic, the grid of the 6C4 oscillator should be at a potential of minus 12 volts. Okay, so right now you see the output of the oscillator on the oscilloscope screen over there, which is a swept IF signal. Anyway, the potential of minus 12 volts, which you see here on the schematic, is measured over there on pin 6. So let me show you. I'm trying to give you a good image of it. So over there. Right. Okay. So that's where we're measuring. And the potential is not minus or negative 12 volts, but is negative, say, almost 55 millivolts. Okay, millivolts, not volts. Now, according to the schematic, it should be minus 12 volts. Yeah. Now, I'm in a bit of a fix here, in the sense that the oscillator seems to work perfectly. Yeah, it gives out a healthy, strong signal of almost half a volt, and I can tune it to any frequency I like, as you can tell. Yeah, and it sweeps marvelously well. So, and it's a very clean signal. So, in my opinion, the oscillator works perfectly. Yet the grid is at minus 55 millivolts and not minus 12 volts. So if any of you can give me a solution to this mystery, it would be most welcome. This is the potentiometer annex switch, power switch, which I need to unmount. Now, as you can see, it's quite close to the power transformer of the sweep generator. So, and of course somebody somewhere in the past mounted an extra preset switch for the sweeper above it. So I'm kind of squeezed between a rock and a hard place here. So I think what I'll do is I'll simply unsolder the power wires, so this wire here and that wire over there, and I need to unsolder, let me see, because the space is a bit cramped there. I need to unsolder, roughly speaking, 3 wires. Yes, 3 wires from the potentiometer. 3 wires and a resistor. Well, maybe even 4. 4 wires and a resistor. Okay? So, yeah, well, let's get to it. I am almost ready, unmounting completely the potentiometer with which to set the sweep width of the sweep generator. And well, I only need to unsolder 3 more wires, and then we'll have a closer look at the action inside the potentiometer. Alright, so I managed to unmount the potentiometer, and it has a code engraved on it. I would say it's 137308. I don't know what that code is. Then there's a parts number code C737 809-9. So I guess these are parts codes that RCA used. Also on the switch there's a little text which says it's a 3 amp 120 volts or a 1 amp 250 volts switch, and the usual patent blah you see on those parts. So okay, well, the thing is, there is a problem with this potentiometer, and therefore I need to open it. Now you'll notice that there are tiny little slots in the just underneath this, you could call it this end cap right here. So you see one slot, 2, 3 slots. So without destroying this part, obviously, I'll have to see whether I can uncrimp the tab which is in this slot so that I can open it up and have a better look. Well, alright, I did not disassemble the potentiometer, and I'll show you why. So there's something peculiar going on, and I have to sort of figure out what the problem is. So if you take a look at the multimeter, which is set in the ohms range, well, let's have a look. If I attach my ohms meter to one end of the potentiometer, yeah, and obviously one of the wires goes to the common. Okay, we're in the 0 ohms range. Okay, so now let me show you what happens when I turn it up slowly. Oh, it is turned up. Okay, here we go. Well, up to now, no problem. Just going on. 5 volts, 6 volts, ohms, 7 ohms, 8 ohms, 9 ohms, and there you are. At the end, 11 ohms. So yes, this is an 11 ohms potentiometer. If you watch the screen of the multimeter, it's 11 ohms. Okay, so let's try the other end of the potentiometer. Okay, here we go. I'm going up and up. 1 ohms, 2 ohms, 3, and it's going smoothly. There are no gaps, and that is the weird thing about the potentiometer, because you'll remember that I disassembled, or rather unmounted, this potentiometer because there seems to be a kind of a, and there you go, 11 ohms, well, 10.9. okay, so there seems to be a weird kind of gap in the vibrating frequency of the special capacitor which is built into the sweep generator down there. Okay, so for some specific and peculiar and as yet unknown reason, the vibrating how should I say, the vibrating capacitor seems to have a gap where it simply stops vibrating for whatever reason, and then suddenly starts vibrating again, but then a lot stronger, or in the reverse. So if I turn it down counterclockwise, then it vibrates strongly, and then suddenly it stops, only to resume, but much less so, quite an end down the range of the potentiometer. So I'm a bit mystified. I just hope it won't be a mechanical problem, because those are really hardest to solve. I unmounted the little metal case I had built from around the impedance adapter annex demodulator module, which is connected to the RF output, as you can tell. Actually, this is the attenuated RF output, whereas this BNC right here is the unattenuated one. Alright, so what I need to do now is to sort of take the diodes, which are part of the demodulator circuit, out of the equation. In other words, I have to try to connect through the RF signal which comes through these coaxial wires straight to the output. Well, not actually straight, but let's say through the components to the output. And well, I'm probably also going to have a look at the signal just to see how good or how bad it goes through this little module. So, because I think I might have to, well, possibly tinker a little bit with it to make it work the way I would like it to work. Oh, and by the way, if you were curious as to how the BNC connector is mounted, well, there you have a good look at it. It's actually a layer of semi-stiff plastic, rather thick plastic at that, about 1.5 millimeters thick, fronted with a piece of aluminum foil. Actually, it's a bit thicker than foil. It's about a 0.5 mil thick aluminium piece of sheet metal, you could say, which was cut to the exact same shape as the plastic backing. And it works nicely. As you can tell for yourselves, it does exactly what it needs to do and nothing more than that. So, well, let's get on with it. I short-circuited the two 1N34 germanium diodes with two little straps of copper wire. I think you can just about see the straps, okay, on either side of the printed circuit board, and they short circuit the little diodes on top. So now I could have made it a lot more elaborate using a switch or something like that, but whenever you're working with high frequency stuff, meaning anything which goes upwards from 1 megahertz, let's say, it pays off to work with as short as possible connections, because every bit of metal or solder has the tendency to radiate out of its electrical part, and that is a phenomenon you should try to keep as weak as possible, okay, because this stray radiation can often induce unwanted effects. So I went for what seems to be the easiest and cheapest solution, but which is in high frequency terms the best one. Okay, so I'm going to reconnect my adapter to the BNC connector you see over here, and I'm going to connect it up to the scope over there, and then we're going to have a look at the signal without the high frequency diodes. Ironically, without the demodulator adapter I had built, the whole thing seems to work just as well. And just to show you the signals, there they are. So the lower signal is the unattenuated one. I mean, it's the one connected to that extra BNC connector which was built in later by somebody. The upper signal is the attenuated one. Now, just to tell you, the lower signal, so that one over there, is set at 5 volts per division. So peak to peak, that would be about 10 volts peak to peak. Now the upper signal covers a little bit less than 1 division, and that is set at 100 millivolts per division. So that would be, say, 90 millivolts peak to peak. So yeah, well, there's a huge difference in signal strength depending on which output I use, the unattenuated one or the attenuated one. Well, I suppose practice will tell which one is most useful. Now, just to show you the dramatic effect that the attenuator has, if I turn the attenuator down, say about a quarter there, then you see the signal is already only half the size, which means it's about 50 millivolts peak to peak. And if I turn the attenuator down about halfway, then the signal is imperceptibly small, and we're talking about, let me see, then we're talking about something like 15 millivolts peak to peak, which is really small. Okay, but in any case, what I wanted to show you, and that is an interesting detail, the lower signal is the unattenuated one, the upper one is the attenuated one. Okay, so if I bring both signals closer together, yeah, so this is signal of the attenuated output, this is the unattenuated one. If I bring them together around the center line, you see that their frequency is the same, although their amplitude isn't, and also they have a phase shift, so which means that the attenuated signal seems to be shifted earlier than the unattenuated one, or later, depending on how you look at it. Still, I would say there is a shift of about 45 degrees between both, which is interesting. Apparently the attenuator, which you'll remember is a slidable, adjustable capacitor, shifts the attenuated signal by apparently about 45 degrees compared to the unattenuated one. Still, the frequency is the same, so whether one or the other is shifted in frequency, I mean in phase, doesn't really matter. I mean, the phase shift has absolutely no consequence on using it with any other kind of circuitry. Now, I also managed to repair the sweep generator. So now I have, as you can tell, full range, full sweep range. Okay, let me show you just one signal, okay? So this is the attenuated signal, and it's completely open now, so it should be maximally unattenuated. And look, I can turn up the sweep as much as I like or as little as I like over the whole range. So now there's no more gap. So it turns out that apparently there was a kind of a bad solder point, which I seem to have solved resoldering and cleaning all the solder points when I resoldered or reinserted the potentiometer. So now it works perfectly. So which should also remind you that you should always keep solder points as clean as possible and make them as solid as possible. So you should have a good flow of solder over the solder point. Anyway, like I said, here it is, all put together again for a final look at it. Well, it's certainly a lot cleaner than when we started out restoring this, and it seems to work properly, albeit unaligned. So, but like I said, as soon as I have the proper BNC pigtail connectors, I might give it another try. In fact, I'm pretty certain I will give it another try to align it. However, I would like to have a good marker generator. I mean, a reasonably professional one. And well, I guess I'll have to save a bit more in order to buy one of these days. But that doesn't stop me of trying to align it with the tools I have. Anyway, just to show you one final time what the outputs do actually. So the IF VF output, which is here, okay, outputs an IF signal, swept or non-swept. So let me show you. So over there on the oscilloscope, we should start to see the signal when there you go, the tubes heat up, and I should be able to see a signal, and there you go. Okay, so with this button you can set the attenuation level of the IF output. So if I turn it counterclockwise, watch the oscilloscope, you see the signal drops in amplitude. Obviously, when the signal drops in amplitude, the oscilloscope has a little bit of trouble of locking on to the signal. But anyway, that's what this button does. And then you have this button, and with this button you can more or less tune the IF signal. So if you watch the oscilloscope screen, you see that the signal starts to get higher in frequency, and when I keep on turning, it drops in frequency once again. Now, mind you, there seems to be a slight gap at a certain frequency, and also the signal isn't very clean at a certain frequency. Now, okay, if I set this button, which somebody in the past built in, to position 1, the IF output is practically unswept. I say practically because it's still swept. If I turn up the sweep width button, well, you can see that the signal is being swept nonetheless, but very little. Okay, if I set the preset button to position 2, then already of its own accord the sweep width is increased. Okay, so, and I can decrease it or increase it as is most useful to the application I'm using it for at that specific moment. Okay, so anyway, that's what this does. This allows you to tune, as it were, the IF frequency. Now, mind you, you have to set the channel button to IF position, okay? Otherwise, you won't get any IF output. These black jacks you see here are just ground connectors, okay? Nothing else. Right. If you switch over to this output here, okay, and you set it, say, to channel 2, then you get RF output. Now, mind you, this was built in at a later stage. So this output here is a later addition, just like this button over here is. You won't find that on a standard RCA sweep generator. Okay, so anyway, this is unattenuated RF. Okay, so you get, as it were, full blast. And let me see. Okay, I'm at 5 volts per division right now, which means that it's a little bit less than 20 volts peak to peak. Say 18 volts perhaps? 18 volts peak to peak, which is a heck of a lot. I can't imagine any decent electronic circuit needing 18 volts peak to peak. Still, that's what you have. So, and we're on channel 2. Okay, so if I go to channel 3, the frequency will increase. Before the battery gave up on me, I was showing you what the IF output did. And then I was getting to this output, which had been added later on, together with this preset button right here. Now, this output here is an unattenuated signal, which is set by this button here, the channel button. Now you can see the output of channel 3 setting over there. It's a pretty strong signal, and as you can tell, I can also set the sweep mode. Yeah, so which is perfect actually. So, like I said, this is the unattenuated mode, and that outputs a signal way much stronger than the attenuated one, which is here. There you go. So this is the attenuated one, but with minimal attenuation. So if I turn back counterclockwise the attenuation, you can see the signal weakening. It's a bit jittery while I turn it, because remember, this is a mechanical kind of setting, not electronic. So even the tiniest little bit of dirt causes a little bit of jitter, yeah, or oxidation. Anyway, there are two more things I did not explain, and which is the blanking and the phase button, and of course also the scope output. Now, these three things are really what you would need to how should I say, to align any sort of equipment with this thing. Yeah, so what you would do is you would hook up the one of the channels of your scope, namely the horizontal channel of your scope, to this output here, and you would set your scope on line input synchronization, which means that the scope gets its synchro signal from this output here. So it doesn't use any kind of synchronization mechanism inside the scope itself. And with this button here, the phase button, you would set the synchronization of the scope signal in such a way that the signal is stable. Okay, so because actually it means that the scope is being synchronized on the, in my case, on the 50 Hertz of the AC. And the blanking is a little extra which they built in, which creates, if you set it to on, well, obviously right now you don't really see what it would produce because there's no demodulation, of course, of the signal. But anyway, the blanking would put a kind of a second line underneath the demodulated signal, and that would kind of give you a reference baseline for the signal, really. So I can't demonstrate this or this right now, or this for that matter, because, well, you would need a kind of demodulation to show you what I'm talking about. Anyway, this is it for now, and like I said, as soon as I get the extra pigtail BNC connectors, I'll probably try once more to align this equipment. Now, mind you, as it is reasonably well aligned. Okay, so let's take channel 3 for example. The alignment would need the output of the sweep generator to be somewhere in the middle of the frequencies you see here. So they say in the service manual it should be the base frequency 60 plus 3 megahertz. So that would mean 63 megahertz. And the signal I'm getting is, let me see, 63.1 megahertz. So it's reasonably well aligned, but I suppose it wouldn't hurt to give it an extra alignment. Anyway, that's it for now. Hope you enjoyed this video. So stay tuned for more to come.